Hello students, we are at our last module. We have looked at all the computer components, memory, CPU, I/O. Now we want to learn how to measure the performance of a computer. Year by year, the cost of computer systems continues to drop dramatically, while the performance and capacity of those systems continue to rise equally dramatically. Today's laptop have the computing power of an IBM mainframe from 10 or 15 years ago. What is fascinating about all this from the perspective of computer organization and architecture is that, on the one hand, the basic building blocks for today's computer miracles are virtually the same as those of the IS computer from over 50 years ago, while, on the other hand, the techniques for squeezing the maximum performance out of the materials at hand have become increasingly sophisticated. In this last chapter, we're going to look at the hardware performance because the hardware performance is often the key to the effectiveness of an entire system of hardware and software. And we cannot just look at one aspect or one performance matrix. Yeah? Different types of application, different system will have different matrix. So we have to look at all the factors in determining overall performance. So we're going to help you understand how best to measure performance and the limitations of performance, which is very important when selecting a computer system. So why do we measure performance? Yeah? Performance measurement is very important because we want to identify what are the problems. It's like, why do we grade students? Why do we have test 1? Why do we grade your lab? Because we want to know, yeah, those students who didn't pass up or those students who didn't get A, yeah, maybe they have some problem. They don't understand the material. So the same thing with computer performance. And we want to compare, yeah, for hardware and software, we want to compare which machine is faster, yeah, which instruction set architecture is better, which implementation is faster. And these enable us to ignore all the unimportant issues if we know exactly what we are measuring. Yeah, so we can expose the significant performance issues. Of course, there are more than one way to measure performance. For example, in your CO project, we measure your teamwork, yeah, your creativity, your critical thinking. So the same thing in these slides, we give you the example of airplanes. So we want to compare airplanes in terms of different performance matrix. For example, in terms of capacity, Boeing 747 can move the largest amount of passenger. Cruising range, the McDonnell Douglas DC, wow, yeah, almost double of the rest like Boeing and Concorde. But speed, of course we know this, yeah, before this we have Concorde. And you know, and if you look, right, there's not one particular airplane that is the best in all the matrix. So if we want to have the best speed, then we of course go for Concorde. But if we want to talk about throughput, meaning, yeah, at what is the best, how many passengers can we transport in terms of maybe in 1 hour, yeah, so we break it down. So in that case, who has the highest one? 747, yeah, the best throughput. If you're a passenger, then you go for speed. But if you are the CEO of an airline company, then you go for throughput. So different measurements for different output. When we talk about computer performance, then in general, we base them based on two criteria: response time and throughput. So response time is how much time is needed to complete an operation. And throughput is how many jobs got completed in 1 unit time. And often, there's a trade-off. So we can trade. Sometimes if we want a faster response time, sometimes the throughput has to be small, just like the Boeing, right? So if you want more jobs to be completed, then maybe the response time has to be longer. So depends what you want in a computer performance. Look at this figure. This is on your left is response time, comparing between Samsung and also Intel and some others. On your right is the throughput. In terms of response time, the lower is better. So looks like Samsung has a lower response time. But if we look at throughput, we want a higher rate. Throughput here is megabyte per second. And also this figure, Samsung has a higher throughput. To maximize performance, we need to minimize execution time for some tasks. A simple example for you, those who run faster means it has a better performance. So this formula, performance is the inverse of the execution time. If you are slower, so execution time is large, means you are slow. That means your performance is slower. So very simple. For performance X to be bigger than performance Y, that means execution time X has to be smaller than execution time. And if we want to say X is n times faster than Y, that means when we compare between performance X over performance Y, you will get how many times it is faster. So if Usain Bolt runs 8 seconds per 100 meter, and I run like 90 seconds or maybe more, so 90 seconds over 9 seconds, so I am 10 times slower than Usain Bolt, which in reality I am like 1 million times slower than Usain Bolt. There are many common performance metrics. The one that we're going to concentrate on are the three that is highlighted. It is CPI, cycles per instruction. Be careful, C is cycles, not clock. Because when we say clock, the measure is seconds. So CPI is cycles per second. IPC is instruction per cycle. And then we have cycles per second. You have seen this before. It's in hertz. So these three, you're going to look at a lot in this last chapter. We're going to start looking at basic computer performance equation. What is the formula to calculate performance? We want to know what is the CPU time. What is it? It is the time spent in the OS or in running the program, where the CPU is actually working for something. Because you know that CPU can also be idle. But here we're talking when the clock ticks and CPU is working. So that is what we call CPU time. The formula is here. CPU clock cycle for one program and U times clock cycle. So don't worry, you do not have to memorize. I always teach my students, please don't memorize. You just need to understand what is the unit, then you get your answer. So in this case, CPU times is in terms of how many seconds per program. So in one program, how many seconds does it take for CPU? to work its magic. We are running a program. So in one program, there is many instructions. So instruction per program. And one instruction can have many cycles. And one cycle can take how many seconds? So if you cancel, you end up with seconds per program there. Very important for you to understand what is given to you. Write down the unit, then you do some manipulation to get your final answer. So what is the answer that you want, and do some cancellation of the formula. Okay, very easy. To achieve better performance, reduce instruction set machine. To get better performance, it reduces the number of cycles per instruction, but for complex instruction set, it actually reduces the number of instruction per program. The key important parameters, I've explained what CPU execution time is. Let's look at clock cycle and clock rate. Clock cycle is the time for one clock period, and clock rate is the inverse of the clock cycle. So if we can imagine that the cycle is 1 cup, so I can say clock cycle is how long does it take to drink 1 cup. So maybe for me, the answer is 5 seconds. It takes me 5 seconds to drink 1 cup. Since clock rate is the inverse of clock cycle, so the question I need to ask to calculate clock rate is, in 1 second, how many did you drink? So it is the inverse, so that will be 1 cup per 5 seconds, which is 0.2 cup. That is my rate. Yeah, so in 1 second, I only drink 20%. So by 5 seconds, I drink everything 100%. So that is the meaning of all the important parameters when we measure computer performance. Let's look at the first formula. So that one is the basic formula that you've seen before, right? CPU clock cycle for a program times clock cycle, and you have this. And because we have hertz, hertz is the opposite or the inverse of this. So if we want to have this formula with clock rate, then we just change to divide by clock rate, right? So because you know clock rate is, what is clock rate? Clock rate is cycle per seconds. So that is why we change from times to divide. Because I'm happy. Clap along if you feel like a room without a roof. Because I'm happy. Clap along if you feel like happiness is the truth. Let's look at one example to calculate CPU execution time. This is the question and the statement. What we need to do is to extract the information. Let's go line by line. So for computer A, first it says here, the program runs in 10 seconds on computer A. What is that? That is CPU. CPU time A equals to 10 seconds. Okay, move on. Which has a 4 gigahertz clock rate. And this is straightforward. Clock rate A equals to 4 gigahertz. I think that's it for computer A. Okay, how about computer B? We'll run this program in 6 seconds. So is that CPU time B, right? And then, given that computer B requires 1.2 times as many clock cycles per program as computer A. Alright, hold it. In computer A, In computer A, it gives a direct information of clock rate. But in computer B, it doesn't give you the clock rate, but it tells the performance of CPU B in terms of CPU A, and it gives you clock cycle. So don't worry, just write down the information. That means clock cycle per program equals to 1.2 times clock cycle per program A. So you have the 4 information. So what does the question want us to calculate? What is computer B clock rate? So I think we can start with computer A because it's straightforward information. So let's look how to calculate this. We continue. So the first thing we need to find is what just now, because we need to find the clock cycle. Right, so we use this formula, the CPU time A, but using the clock rate instead of clock cycle. So we fill up the information. CPU time is 10 seconds and clock rate is 4 gigahertz. We convert that to 4 times 10 to the power of 9 hertz. So we end up with this answer for clock cycles per program for A. Then we can calculate clock cycle per program B because it says that it is 1.2 times clock cycle per program A. So we got that. And our answer is for clock cycle per program B, this is our answer. Do it methodically, okay? One by one. Don't jump any formula, any calculation. Do it step by step. Once we have clock cycle per program B, then we can calculate, it asks for clock rate B. So use the formula again, CPU time B. We know CPU time B. Yeah, we know CPU clock cycle, which is from here. Then we can get our clock rate. So use the mathematics that our primary and secondary teacher taught us. We end up with this calculation and we finally get our clock rate. Yeah, so please, I advise you, don't skip any lines of calculation step by step. So that's your answer. The second formula we're going to look at is the IPC, instruction per clock cycle. So let's have a look at the previous formula that we learned. Yeah, CPU execution time for a program is CPU clock cycle for a program divided by clock rate. Now to use IPC in the calculation of CPU execution time, we can use this formula. It is actually IPC times clock rate. Again, don't have to memorize, but let's look. What is IPC? IPC is instruction per cycle. So instruction per cycle, and clock rate is cycle per seconds. So we can cancel out cycle. That's why we end up with instruction per second. So that's how we use IPC. Next, the third formula is CPI. What is it? Clock cycle per instruction. So when we say instruction count, we actually say instruction executed for the program. What is the formula? We do here instruction count times CPI times clock cycle. Oh my god, I'm confused. Doctor, what is this? What should we do? Take a deep breath and write down the formula in terms of the unit. So this is instruction count per program. So instruction per program times CPI is what? Clock cycle. Cycle per instruction. And Clock cycle time is seconds per cycle. No memorization, right? Just look at the term, write down the formula, the unit. Now you can cancel. Instruction, instruction. What else? Cycle, cycle. So what do you end up with? You end up with seconds per program, which is what CPU execution time is. If we use clock cycle time, we can also use clock rate, and this is the formula. Easy, isn't it? In example 2, we want to calculate using CPI. So suppose we have two implementations of the same instruction set architecture, ISA, and for the same program. Same program but run in different computer, A and B. So for A, clock cycle is 200 picosecond. For B, clock cycle is 500. So just in terms of clock cycle, which one is faster? A is faster because you only need 250 picoseconds per cycle. But yeah, in terms of instruction, computer A needs 2 clock cycle per instruction. Computer B needs 1.2. Okay, now you have so many formulas given to you. What should you use? CPU time, clock rate, clock cycle, IPC, CPI, what? Okay, don't worry. What did I tell you before? Yes, formula, extract the formula. First, what does this mean? Clock cycle, what is the unit? Picosecond per cycle. So that is seconds per cycle. How about this one? CPI. What is the unit? This one is cycle per instruction. So can we cancel anything if we multiply? Yes. Cycle at the top, we can cancel with cycle at the bottom. What do we end up with? We end up with seconds per instruction, meaning for one instruction, how many seconds? Then we can compare to answer the question, which computer is faster and by how much. So first, let's get that seconds per instruction for each computer. So at computer A, so this is the formula. Just use seconds per cycle times cycle per instruction. We cancel cycle. So we get for computer A, it takes 500 seconds per instruction. For computer B, we end up with 600 seconds per instruction. So now we have the same unit, seconds per instruction. So which computer is faster? Which one? 500 or 600? So computer A is faster because 500. So computer A is faster for this question. But by how much? So obviously, A is faster, but by how much? Compare the performance. So we compare performance A over performance B, which actually means the execution time, so we reverse it. So in execution time, we get B over A. So we end up with 1.2 times faster. Simple, no memorization. All you need to is understand the question, extract the information, see what manipulation you can do to get the answer. You're okay. Sometimes it is possible to compute the CPU clock cycles by looking at the different types of instruction. And we don't only have one type of instruction with one clock cycle, with uniform clock cycle. Sometimes we have different instruction will have different clock cycle. So with that, we have a special formula, this one, where it will look at the number of instruction and the cycle CPI for that particular instruction. So let's look at an example to get you to understand better. A processor has 3 classes of instructions. One processor, 3 classes of instruction. Instruction A, B, and C, and different CPI for each instruction class. A CPI is 1, B is 2, C is 5. And then what is this C? C is the count of the number of instruction of class. So for that particular class A, how many instructions are there? So these are the numbers. For example, for class C, code 1 has 1 instruction, code 2 has 2 instructions. The question asks, which code sequence is faster? I repeat, we have 2 different codes running on the same processor. These 2 different codes is running the same number of classes. So different segment, different classes, A, B, C. Code 1 have A, B, C. Code 2 has A, B, C. But because they are different code 1 and code 2, each classes have different instructions for different code. So the question asks which code sequence is faster, but first we need to answer how many instructions for each code. So we total up. When we total up, we get for code 1, for the 3 classes, it has 9 instructions. And for code 2, it has 7 instructions. Yeah, so it looks like code 1 probably has, because it has more instruction, maybe it is slower because code 2 has only 7 instructions. But yeah, we need to consider clock cycle. So what we do is we times 5 and also this we times. Yeah, we time and we time, so we get these numbers and we total them up to get the clock cycle. So it says here code 1 has 9 instructions but using 16 cycle, while code 2 has 7 instructions while using 17 instructions. So what is the conclusion? Code 1 is faster because it uses 16 cycle only compared to 17, even though it has 2 more instructions, 9 compared to 7. So this is how we compare when we have different classes of instructions with different cycles per instruction, CPI. These are the summary of performance equation. No worries. Understand what the formula is, what the data means, get the unit, do some cancellation, you get your answer. The second page. To remind you again, there are several factors affecting the CPU performance. It could be algorithm, programming language, compiler, instruction set architecture, ISA. And what do they affect? Most probably, if you look, most of it is instruction count, CPI, and also clock rate. So these are the terms in the part 1. So in conclusion, for CPU performance, it depends upon many factors. It could be pipelining, parallel execution, integrated floating point, branch prediction, and we can also optimize our user code. That is the greatest opportunity for performance improvement. So in terms of how we do loop manipulation, and most importantly, good algorithm design. That's it, boys and girls, the end of computer organization and architecture. After this, let's concentrate on your COA project. Peace and out.